All right. Hello, everybody. Thanks for coming to the makeup lecture. I said in the email, but I think we are going to have this hopefully only one other time, at most two other times. So, for the makeup lectures, we'll use this one, and for the regular Monday and Wednesday ones, we'll go downstairs. All right. So last time we discussed about heat equation in 1D and derived a simple finite difference approximation scheme to solve the heat equation in 1D. How many of you have already tried it? Oh, very good. Most of the class. Nice. How did it work? Works well? Good. So that means what we are doing is useful. So today, first of all, I'm going to extend a little bit of what we did on Wednesday into different types of equations, elliptic and hyperbolic equations. Then I'm going to discuss about approximation error, or how much error we are making by using the finite difference approximation instead of solving the PDE exactly. And then, in order to link the approximation error to the solution error, so the approximation error is actually, we're going to see, not what we care about. We care about the error in the solution. We care about the quality of the solution. And the critical link between approximation error and solution error is stability. And I'm going to talk about stability. And I'm also going to talk about how to build a scheme. So instead of a scheme like given to you, I'm going to teach you if you encounter a differential operator you've never seen before, how do you build a finite difference scheme for that operator? Or if you want to build an operator for some differential operator you have seen, but you want to build one that is different from the conventional ones to satisfy some additional requirements you need in your research or something, then I'm going to teach you how to build a scheme for yourself. And then I think we will have time to discuss a little bit on the two-dimensional stuff. All right. Okay. So first of all, let's review a little bit what we did in the first class for heat equation. So we have been looking at partial u, partial t equal to a kappa times partial square u, partial x square. And basically, we approximate the right-hand side. Okay, so we're saying for a particular spatial location, right? We discretize the solution. We discretize the space x into grid points. And the spatial location of the grid points are x1, x2, x3, etc. And we also discretize the solution u into the value of the function u at the grid points. So the value here is u1, the value here is u2, the value here is u3, etc. And we approximate the derivative. Now it's no longer partial derivative because each ui does not depend on space. It's just a function of time. So the ordinary derivative of ui with respect to time is approximated by the same kappa times ui plus 1 minus 2ui plus ui minus 1 divided by delta x squared. All right, where delta x is the spacing between adjacent grid points. And here we assume we have a uniform spacing. All right. In finite difference, it's very common to see uniform spacing. If we have to use a non-uniform spacing, it is actually, a lot of people would rather go to finite volume or finite element, because in finite difference, it becomes a lot more complicated to have a non-uniform grid. Okay, so let's look at this approximation. We can practically use the same approximation for elliptic problems. For example, let's switch to another color. for elliptic problem. For elliptic problem, for example, I want to solve this equation equal to f. All right, where the f is a function of x, is a given function of x. I want to find out what solution u has a second order derivative equal to f and also satisfies certain boundary conditions. So this is equivalent to, let's say, if I have the heat equation but add a source term that is, let's say, of g of x, right? Then I can discretize the function g also into the value of the function g at the grid points. Then here, I can approximate the right-hand side using the same differential operator, but then plus g of I. That is a consistent discretization of the equation. G is only a function of space. Yes. 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 Elliptic. Right. Elliptic equation is an equation that doesn't depend on time. So this equation is only an equation in space. It has no time in it. Okay. So for this equation, we can think of having this heat equation with a source term and evolve the heat equation to time equal to infinity. Evolve the equation into steady state. Then I'm basically saying, if I have a steady state, then the left-hand side, partial u, partial t, is equal to 0. And then I'm basically solving the equation kappa times partial square u, partial x squared plus g equal to 0. And if you basically set a g equal to minus f times kappa, then we are solving this elliptic equation. All right. And if you think of, again, last time we have written this parabolic equation into a vector form. So du vector over dt is equal to a matrix A times the vector u. In this case, I'm going to also plus a vector g. Okay. Then, if you think of the elliptic equation discretized using exactly the same discretization, it can be written as, or maybe I need a kappa here, then it can be written as the same A times the same vector u, the same unknown solution u, is equal to a vector f. And instead of using ODE 45 to solve this ordinary differential equation, I can use backslash in MATLAB to solve these linear systems, right? So basically, if I say f vector is equal to f1, etc. to fn, well, with the boundary condition, I think I only need from f2 to fn minus 1 because f1, because u1 and un is already known. It doesn't have to be in the equation. Then my u is equal to a, I'm just going to write in MATLAB format, backslash f. Or if you want to write in like a more mathematically acceptable way, it's a inverse times f. But in MATLAB, it's a better idea to actually say inverse of a times f, because MATLAB has much better schemes to solve linear systems than inverting a matrix. Inverting a matrix is fundamentally a more complex and less stable algorithm than solving a system of linear equations. So if you do backslash, MATLAB is actually solving a system of linear equations without actually constructing the inverse of A. But if you do inverse of A times F, then you actually compute the inverse of A, which is a much less, it's a worse algorithm to use than solving the system. All right. Any questions on this? So we discussed we basically used the same finite difference method we studied last class to solve this elliptic equation. All right.